unitary skew adjoint. It's a Clifford multiplication by the conormal to the boundary. And then correspondingly, we can split our spinors into the positive and negative ones according to the plus minus I eigenspaces of that. And then the Dirac operator takes this familiar form that you see on the slide in the center. And in particular, that operator D has this particular form here, which is the Dirac operator on that even dimensional boundary. And the D minus and D plus are adjoints, or formal adjoints of each other. So the classical cobordism theorem then says if an even dimensional manifold with a Dirac operator is a boundary in this sense, D plus and D minus, then the index of the Dirac operator there is 0 between the various bundles. So this is the cobordism theorem, the classical cobordism theorem. And it used to be the basis of the very first proof of the Atiyah-Singer index theorem before other proofs were found. Next slide, please. All right, so the classical proof of the cobordism theorem has always been perceived as being difficult at the time. It's contained in the Palais seminar. It's a chapter written by Seeley and Palais. And it uses the classical boundary value problem theory and the Calderon projector. But over the years, many different proofs and generalizations have appeared. So I will point out a few of them. One proved by Hickson is similar to what Victor was just talking about. You're attaching an infinite cylinder to the boundary. And so you are working really on a complete Riemannian manifold than a manifold with cylindrical ends rather than a manifold with boundary, which is incomplete. So this removes a lot of the boundary value problem theory. And he was able to prove, doing the analytic part on that manifold with cylindrical ends, to prove the cobordism theorem. A somewhat related but different proof that I will go over a little bit later is due to Lesch, which is a similar idea. So instead of attaching a cylinder to the boundary, you're attaching a generalized cone where the link is the original boundary to that cylinder. And then the analytic part is, again, no longer classical boundary value problem theory, but you're working with cone operators and manifolds with conical singularities. There's other approaches by Nicolaescu, Braverman, Moriano has a generalization to manifolds with conus and cusp operators. So a purely K-theoretical proof by Katerina Carvalho appeared in 2005, and there is generalizations to Kasparov theory, non-commutative geometry, so the KK-Bordism theory by Michel Hilsum. So what we are going to do here is we are reviewing and generalizing Lesch's proof. And the motivation to do so comes from index theory on manifolds with singularities. Next slide, please. So in order to understand what's going on, we have to remind ourselves about some of the basics from the extension theory of symmetric operators. I'm going to go quickly over that. So we have a complex separal Hilbert space, which is, of course, an L2 space. Here we have an operator A, which you can think of as a Dirac operator, which is symmetric and densely defined initially. Then, of course, it's a closable operator. We have a symmetric closure, which, function analytically is just the double adjoint of A. This is the minimal extension, the closure of the operator A. The maximal extension is just the single adjoint, acting on, again, with its functionality domain, the domain of the adjoint, the maximal extension. And the maximal domain is a Hilbert space, of course, with respect to the graph in a product. Next, please. And what happens is, of course, this is why it also gives the name. So the minimal domain is the smallest, the maximal domain is sort of the largest domain you have for extensions of this operator D. All the extensions, the closed extensions, have domains in between. And you can think about that quotient, the maximal by the minimal domain, as sort of an abstract Cauchy data space. So this is a functional analytic framework to encode boundary conditions, if you will. A key towards understanding what is going on is the adjoint pairing we have in this situation. So this is just, green identity, if you wish, integration by parts. Gives a specific formula. So this this is the pairing, and modulo the minimal domain, this is non-degenerate. And the extra 1 over I that I put in front of it is just to go from a symplectic form to a Hermitian form. So this is basically this is an indefinite inner product space. So a Hermitian sesquilinear form on that quotient, non-degenerate. And the key, so this is basically what makes the advantage work in conic geometry, Lesch's proof over the classical proof. So typically in classical boundary value problem, the Cauchy data space is infinite dimensional. You have boundary traces, you have to understand it this way. While in conic geometry, that abstract Cauchy data space is finite dimensional, and that removes a lot of the difficulties. Next, please. So when you have such an indefinite inner product space, there are two invariants, of course, associated with that. So this inner product is, positive or negative definite on certain subspaces. And you're taking the largest dimensions of subspaces where it's either positive definite or negative definite. So these are numbers. And those are the invariants of the structure. And when you're looking at indefinite inner product spaces of this kind, and then you, of course, have a notion of isomorphisms that respect the structure, so unitary isomorphisms in this sense. And of course, these invariants are being preserved. And an important quantity that will be interesting us here is the signature of such a space, which is just the difference of the positive and the negative invariants. And classical von Neumann theorem just tells you that those invariants are nothing other than the deficiency indices of that operator, so the dimensions of the eigenspaces, so plus minus I eigenspaces of the maximal extensions in essence. So you can actually use a lambda there. It doesn't have to be plus minus I. Next slide, please. So one thing that matters for what we're going to do is when are those deficiency indices finite and equal? And there is a very nice and simple position here. Namely, if your initial operator there, your minimal extension happens to be Fredholm, or which is another way to check that is if the maximal domain embeds, so the domain of the adjoint embeds compactly in your basic Hilbert space, then you have finite and equal deficiency indices. In particular, the signature of your inner product space there of your Cauchy data space with the adjoint pairing vanishes. So this is very, very simple. The answer, so think about if the minimal domain is Fredholm, then by openness of the Fredholm operators, you can actually add a plus minus I lambda for a lambda to that remains Fredholm. And then for lambda small enough, this is just computing the finiteness and the equality. So stability properties of the index. That's all there is to it. It's a one-line argument, really. Next slide, please. So let's just review then how Lesch's proof of the cobordism theorem works. So as already mentioned, he begins by attaching a generalized cone to the boundary. So this gives this picture you see here on the slide. And he's extending the Dirac operator to that conical neighborhood as follows. So you see here how it looks like on the bottom of the slide. So particularly you're picking up that singular weight factor x to the -1 that you have there, and that also corresponds to basically the tangential part. If you multiply that through, picks up that singular factor x to the -1. That is how this works. This is how you extend it. Next slide, please. And you have a local model, of course, near that conical singularity that you have artificially introduced here. The local model is an infinite cone over that boundary, over that link. So really, it is the inward pointing half of the normal bundle to the boundary. But I mean, you're thinking about this as a model cone, an infinite model cone that you have. And there, on that infinite or non-compact configuration, you have the indicial or model operator, which is in our situation here, due to everything being product by assumption, nothing other than the local form of your operator near the singularity, but now you're looking at it on that infinite sized model cone. So this is the indicial or model operator associated to that artificial conical singularity that you produced. Next slide. Now, then Lesch's proof is based on 3 ingredients. So the first one is global on the manifold. So he proves really this is elliptic regularity that the maximal domain is in some weighted Sobolev space, so you gain some weight near the boundary. So in particular, the maximal domain embeds compactly into L2. Or he also proves then, which is a consequence really, that the minimal domain is Fredholm. And the minimal extension is Fredholm. So this is basic analysis on conic manifolds. So this is where the analytic meat is. And by what the theorem that just reminded, proposition I just reminded you about from extension theory, that tells us that the invariants are finite and equal. In particular, the signature of the adjoint pairing on the manifold vanishes. The second ingredient is, and that's another elliptic regularity statement. So if you look at a function, the maximal domain, and you multiply it by a function which is supported away from the conical point, well, then you are in H1 with compact support away from the boundary and singularities, and that, of course, is in the closure of the operator. So what this says is, as soon as you localize away from the singularity, you end up in the minimal domain, and that in turn says, if you localize near the singularity, that every function, the maximal domain, has a representative which is compactly or supported near the singularity modulo the minimal domain, which is really just multiplication by a bump function near the conical singularity. And when you look at that, when you look at this map, which localizes near the singularity here, you're getting an isomorphism between the inner product or the adjoint, the Cauchy data space on the manifold with its adjoint pairing, and the Cauchy data space on the model cone for the model operator with the adjoint pairing. So this is an isomorphism of the structure. And in particular, the invariants then are preserved. So what this tells you is that the deficiency indices localize. So the deficiency indices of the operator on the manifold and the deficiency indices of this operator, initial operator on the model cone, they have to agree, they have to match. Next slide. And so you can compute them on the model cone. And on the model cone, you take advantage of this particular form of the operator. You are computing the plus minus I eigenspaces of A maximal A acting on your L2 space. And you take advantage of the spectral decomposition of the tangential part of the D minus D plus part of the operator on the link. You just compute it. And this gives you here formulas for the deficiency indices on the model. And you see here the null spaces, the kernels of D minus and D plus contribute to the various deficiency indices. And then there is an offset that has to do with the small eigenvalues of the tangential part, which is the same for both eigenspaces. So this number L is the same. So in conclusion then, when you take the difference of the deficiency indices, so when you compute the signature of the operator on the model cone, you're computing, according to this formula, the index of D minus. But the signature of the operator on the model cone matches the signature of the operator on the manifold. But on the manifold, we have seen that the signature vanishes, and so the index vanishes. So this is how Lesch's proof functions. Next slide, please. So a motivation for generalization is we would like to consider more generally pseudomanifolds or manifolds with singularities. And I will speak about the model situation here mostly. So think about this model cone situation we just looked at, but think about that link manifold Z having also conical or edge or more complicated singularities. So this configuration now is in and by itself also singular. So when you're looking at the Dirac operator, then the tangential part or the operator on the link, the D minus and the D plus part, they will not just be operators on a closed manifold, but they actually are operators on a singular manifold, and they themselves have already boundary conditions associated with the singularities involved there. So they're still going to be adjoints of each other, but there are boundary conditions associated with them. And that's a situation that Albin and company have looked at over the past 8 to 10 years for the signature operator and actually worked that out in detail. Next slide, please. So we take that as a motivation to just look at the model situation, initial operators systematically. And I will actually, go away from just the Dirac case, but look at operators of any order. So an initial operator abstractly is a differential operator with operator coefficients of this kind. So we are completely addressing this function analytically. So there's Hilbert spaces E0 and E1 involved. What is E0 in the specific case? Well, that's going to be your L2 space on the link manifold, whatever your link manifold is. And your E1 happens to be a space that encodes the boundary conditions that you already have picked for the tangential part. So this is a space that encodes sort of the lateral boundary conditions of that model cone. So that's in there. With such a thing, we have its Mellin symbol or the initial family, which you get by replacing the derivatives x dx by a variable sigma. And this is the analytic backbone for this, as we shall see. So this is a family of operators then acting, you should think about this as acting unbounded in this Hilbert space E0, but it has a common domain, which encodes the boundary conditions E1. Next slide, please. On that model cone, we can take advantage of the natural scaling action, which just showed up in Victor's talk as translation, but in our picture, we actually have dilation. So we have an R+ action on that, and if we are normalizing that appropriately, it's going to be unitary. And the point is our initial or model operators are almost translation invariant with respect to that. So they're almost invariant in the sense that it satisfies this fundamental identity we have here. So pure translation invariance would be absence of that factor rho to the m, but it actually is there because of the singular coefficient. So we have almost translation invariance up to this power up in front. And as turns out, this is really everything that drives it to some extent. So you can understand the extensions and the adjoint pairing really purely in terms of this identity. Let me just go over that in the next couple of slides. Next, please. So really, as I mentioned, you can look at it purely from a functionalistic point of view. So you're thinking about just some Hilbert space, wherever you got it, which is, of course, we're thinking about the L2 space on the model cone for this. We're having an abstract scaling action, which, of course, we think about as dilation action. So this is now plus action on our Hilbert space, which strongly continuous and unitary. And as such, it has a generator. I'm using here Stone's convention. So our generator is self-adjoint, not skew-adjoint. And in case of the dilation action, of course, that generator is nothing other than x dx. Yeah. So we have a generator in this sense. Our model operators that we just looked at, so they're defined initially on some codomain DC. And they satisfy the fundamental almost invariance property that we just saw, the fundamental almost commutativity with the scaling action. So you're looking at something which is purely abstract, and that's it. Next slide. So then, of course, this is all trivial, but it's important structurally. So your scaling action restricts to nice scaling actions on both the maximal and minimal domains of your operator after you extended that. It's no longer unitary there, so it has some different estimates, but everything basically is preserved. And the most important part of it going forward is that you also have it on the Cauchy data space. So you're getting a dynamical system on the quotient of the maximal by the minimal domains and a plus action on that. So this is the residue of scaling on the model cone, but now acting on the Cauchy data space. Next slide. And on the Cauchy data space, of course, it being in a plus action also has a generator. In our situation, our Cauchy data space is finite dimensional. This is satisfied for our initial operator. So in particular, the generator is just a linear map on the finite dimensional vector space. And so it has eigenvalues. And those eigenvalues refer to this as the extension spectrum of our model operator. And we're going to see in a moment why, because it tells you something about what's happening. So the eigenvalues of the generator of the dynamical systems are going to play a role. Next slide. So Lesch's proof was all about the signature of the adjoint pairing. So we're going to take a look at the adjoint pairing in this context. Again, purely abstract. So we have this. And again, on the Cauchy data space, we're getting a non-degenerate Hermitian sesquilinear forms, an inner product. And because of the almost scaling invariance that we have, when we look at the dynamical system on the Cauchy data space, so the induced action, that's almost, again, a unitary action. So again, it wasn't quite unitary because we had that extra singular factor, but it's almost unitary, except for a scalar factor here, which is, again, just this power rho to the m. So when you're offsetting it, when you're offsetting your generator and shifting by that factor, you're actually getting something which is unitary in this indefinite inner product space. And so the generator of it is going to be self-adjoint with respect to the indefinite inner product, which comes from the adjoint pair. So we are now in a situation where we have sort of a self-adjoint linear map. But we are not in a standard Hilbert space, but in an indefinite inner product space. But nonetheless, there is a spectral theorem for that, and the spectral theorem then tells you everything about the adjoint pairing. Next slide, please. So this is how the eigenvalues of the generator on the abstract Cauchy data space look like. So they all fall inside a little strip in the complex plane underneath the real axis. The strip has width m, as you see. M is that magic number that corresponds to the singular factor. In the Dirac case, m is 1, just to mention that. So it's first order there. The eigenvalues, they come, as you see, in pairs. So they are mirror images about the center line here of that gray strip. And what happens is when you're looking at the adjoint pairing and you're looking at the generalized eigenspaces of the generator, then what happens is only the eigenvalues, only eigenspaces associated with eigenvalues that are mirror images across that center strip, center line here, they paired non-trivially. So if you take an eigenvalue on that strip and you pair with somebody who's not a mirror image, then it pairs to 0. So we have orthogonality of the adjoint pairing there. And what is going to be important are the ones that are on the center line there. This is why I highlighted them in red. So there's the eigenvalues that are just in the middle. And that means this mirror image pairing, that they pair internally to one another. And as turns out, these are the only ones that contribute to the signature eventually. There's more that you can say about the format here. So what this really is, it's a green formula. This is a functional analytic, or rather a linear algebra green formula for the model operator. So the next slide then tells you a little bit about how this works. So this is not going to be that important for us, but it's going to say here, when you're looking at eigenvalues that were mirror images that are off the center line, so really pairings like this, then you find nice Jordan canonical bases that only matching blocks pair non-trivially with matching blocks, so there's more orthogonality in there. And when you're looking at a block that pairs with a matching block, you can actually arrange the bases to look like this. Then the inner product looks like the SIP matrix here. So you're getting a very, very specific simple form of the green formula. And the one thing that matters, which is on the next slide, is what happens with these red eigenvalues that used to be on the center line. So one more slide. Yeah. So these were associated to the eigenvalues that pair internally on the center line. So you also find, Jordan blocks, and the Jordan blocks pair with themselves internally, non-trivially. Across different Jordan blocks, you have vanishing. But here there's a little bit of a dichotomy, a sign dichotomy. When you pair these Jordan blocks, some of them will look like plus these SIP matrices we just looked at. So some Jordan blocks will get a plus SIP matrix in the representation of the adjoint pairing, while others corresponding to the blocks will pick up minus signs, and you count. So for each Jordan block of any signs, you count then how many plus SIPs you get in the representation and how many minus SIPs you get. Those numbers are invariants of the structure. They're called the partial multiplicities. And again, when you take the difference of them, you're getting the so-called partial signatures. And the algebraic signature formula for the Cauchy data space with the adjoint pairing is then only picking up terms from the center line, so the red eigenvalues that we just looked at. So only the ones on the center line, everybody else is out. It doesn't contribute to the signature. And every eigenvalue there only contributes actually the odd partial signatures, as you can see. So this is all plain linear algebra, the canonical form theorem in this context. So we do have a formula in particular that says that a lot of the stuff that is in the Cauchy data space is just invisible for the signature. It just goes away. This is the part that remains. Next slide, please. Now, I will not go over this because in the end of the day, we want to apply that to our operators and not just to abstract functionality gadgets. So there is some analysis involved, and that analysis is being articulated in terms of the initial family. I just want to say here that this laundry list of assumptions on the initial family is about as minimal, in my opinion, as you can get. So it does not, refer to, having Laplacians or anything to give you scales of spaces. This is just internal to what this sort of operator looks like. So it's a minimal laundry list of properties. So under these assumptions, again, I'm not going to go over them. We can actually apply all of this to initial operators in this context. Next slide, please. The only things that I want to point out is, as you would expect, that your initial families are holomorphic Fredholm families. They're invertible then outside discrete set of points. Each strip of finite width only picks up finitely many of these initial roots, so the poles of the inverse. And it so happens, of course, that in the strip that we have previously seen with the generator of the scaling action on the Cauchy data space, so the initial roots, they just coincide. This is exactly what this extension spectrum was in this context. In particular, we see again those red eigenvalues on the center line, which are now the initial roots there. And what happens also is this initial family, when you restrict it to the center line where the red eigenvalues are, this is a self-adjoint Fredholm family there. So along the center line, the P of sigmas are self-adjoint, invertible outside those, in this case, these three red initial roots. So this is very nice. In particular, we have seen that the red eigenvalues seem to play a role for the signature. So this seems to suggest that there should be a relation between the signature of the Cauchy data space and the initial family on the center line. And there is, this is the next theorem, or the next result. Next slide. So along the center line, our initial family is self-adjoint Fredholm. And for self-adjoint Fredholm functions, you have an invariant, the spectral flow. And indeed, it turns out that when you're looking at the contributions, the algebraic contributions from the initial roots or the eigenvalues, which were the differences of these odd partial signatures you have, this is precisely the contribution of the spectral flow as you are crossing such an initial root. So again, your initial family is self-adjoint invertible outside the initial root, so the spectral flow picks up a term as you're crossing over an initial root. And what you are getting is precisely the sum of the odd partial signatures. Is what you're getting when you're running across. And in particular, you get an analytic formula for the signature of the adjoint pairing of such a model operator, which is then the sum of the contributions of the spectral flow across your 3, 4, or however many initial roots you have in the center. So in total, the spectral flow is of the initial family along that center line is the signature of the adjoint pairing. So this is the analytic side of it for such an operator. So this is very nice. And it allows us now to take a different look at the cobordism theorem, which happens on the next slide. So now what we should think of, you see this conic thing up there, but you should think of this M as having more singularities than they appear. I was just not able to draw them. In particular, your Z, your link manifold, has singularities as well. So again, we are thinking about a Dirac operator, or now more generally, some closed symmetric Fredholm operator. And I say a min, but I want to point out that this is not the extension from compactly supported functions. A min already has boundary conditions away from that conical point P, which you have picked up along the manifold already. So there's boundary conditions away from that conical or corner point P already chosen. And they are encoded in this operator A min, which makes it closed symmetric, and which is the analytic input Fredholm. So again, by this is similar to what we talked earlier about Lesch's proof, that in particular implies that when you're looking at the deficiency indices of this operator A min, they have to be finite and equal. So that's particularly we have already vanishing signature for A. The next thing that we need, that near that conical or corner point P there, again, your operator is captured by the model. And again, the model A wedge now is just of this kind we discussed. So there is boundary conditions, lateral boundary conditions in it. Yeah, so A wedge comes with boundary conditions. And the initial family then, the laundry list of assumptions that I didn't go over are supposed to be satisfied in this way. And third is that the boundary conditions you have been already chosen away from that corner point, they should already be self-adjoint. So there should be good boundary conditions away from the corner point. And so the only additional boundary conditions you might pick up are associated again with that corner or point P. So this is again a localization statement. When you're looking at the operator on the manifold and at the model operators, you should be able to localize in the neighborhood. So everybody has a representative right there. So again, your signatures of the model and the signature of the manifold remains preserved. And in these situations, then the cobordism theorem reads as follows: the spectral flow of the initial family that you get. So you have an operator that bounds, so that the initial family is the bounding structure. The spectral flow has to be zero then. So this is the form that the cobordism theorem takes in this context. And just to wrap it up, I'd like to talk about an example, the Dirac operator case on the next slide. So if you look at the Dirac operator again, but now think about minus and D plus already equipped with boundary conditions. So they are adjoints of one another, but there are boundary conditions happening. So then the initial family for the Dirac operator just looks like this. So this is how it is. Your domains, there is some compact embeddings into a basic Hilbert space, L2. And you see here that for real sigma, you're self-adjoint. And by squaring that P of sigma, you see that this has to be invertible outside sigma is equal to 0. So sigma is equal to 0 is the only initial root for this thing along the real line. And so the spectral flow will only pick up something as you're crossing sigma is equal to 0. But when you're crossing sigma is equal to 0, it's a trivial computation to just see, okay, what you're getting there is nothing other than the difference of the dimensions of the kernels. So you're picking up the index. So in this way, you are generalizing the cobordism theorem to first of all, operators of higher order, and you can deal with more complicated situations where you already have boundary conditions away from singularity picked up. So thank you very much for your attention.
Unmute myself. Thank you, Thomas, for your talk. Nice talk. Are there any comments, questions? Go ahead, Elmar.
Sorry, just let me put on I'm trying the camera. Sorry. Thanks for the very nice talk. What I find interesting, you don't have to know basically anything about the operator on the cross section.
It is encoded in the assumptions on the initial family. So if you want to go back, this is a slide that I basically skipped because it has a lot of estimates on it. Anton, can you go back to
But that was very general, right? Just
yeah, it is essentially a black box thing, which also surprises me. It becomes essentially a black box argument. Yeah, it is true.
I find it really surprising. So you don't have to develop a calculus or anything.
No, they don't have to develop a calculus or anything. It is really just the adjoint pairing. So the fact that the spectral flow is being computed in this way, there is a famous result by Robin and Salomon in the 90s about the spectral flow. They realized that under non-degeneracy assumptions, you can compute the spectral flow in terms of crossing forms, so-called crossing forms. So they said, okay, you have a singularity, but your derivative is non-degenerate, your first derivative, and then you can compute a crossing form, signature of crossing forms gives the spectral flow. And what this here does, to some extent, is it looks it looks at real analytic crossing points. So it doesn't require the strong non-degeneracy of the crossing form that Robin and Salomon have, but we have analyticity here along the center line. So we have real analytic singularities for the initial family, and the idea of the crossing forms, this expands and generalizes to these partial signatures. So you can actually make that work. It's a crossing form computation of the spectral flow, which happens to just coincide with the adjoint pairing. I think this is very nice. So and it just matches with the Dirac operator. So with the Dirac operator, you just compute the index, but something which works in full generalities, which becomes basically a Cobordism invariance of the spectral flow statement. This is what it is. So if you have a self-adjoint operator that bounds, you have an additional family associated with it, and it happens to your boundary, then the spectral flow has to vanish. This is what it says.
Okay, any other quick questions or comments, please?
Can I say one comment? Can I say
Please,
one
go
comment?
ahead.
Yeah. It seems there's one more proof of Cobordism invariance of the index in the spirit of topology, namely using K-homology exact sequence. So this talk is perpendicular to that. So here you deleted all topology, yes, but there is a topological thing in terms of analytic K-homology. So
yeah, I apologize for deleting the topology, but yeah, but there is a K-theory proof by Caterina Carvalho also. This is devoid of any of any analysis really. It's a purely K-theory proof from 2005. So there are topological proofs of that, but historically it's an analytic proof. Yeah. Yes.
But maybe both your proof and that could be combined, and maybe there are some similar things. Because when you have boundary conditions in the interior, in the main part, then you have a relative K-homology class, and I think so. So there should be connections.
Is this related to Michel Hilsum's Cobordism triples? So Michel Hilsum
maybe,
has a paper 2010.
Maybe, or Baum Douglas, this Baum Douglas, where they have this. Yeah. Okay. That's my
opinion. Thank you. Thank you for pointing that out.
Okay, very good. And well, I'm not sure we have time for more questions because we are past our time. So I suggest we thank Thomas again.
Thank you.
And
let's